In this video, we're asked to compute the exact area bounded by y equals tangent x and y equals x on the interval 0 to pi over 4. So just to identify our two functions real quick, the straight line is y equals x. And I can see that's passing through the origin and the point 1, 1. And the curvy thing is the tangent function. And the tangent of pi over 4 is 1. And I see that right here where I've marked the boundary of my area. Then I look at a little slice of area that's an area increment that we would normally call dA. And the width of that is called dx. And then the area of it can be expressed as a product of its height and its width. So I need to express that height in terms of the given functions. The height needs to be a positive number here, so the function on top is the one I take first in the difference. And my height is going to be tangent x minus x. So I get an area contribution of tangent x minus x, that's the height times the width, dx. And all that's left to do is sum these up. So the total area is the sum of all the area contributions. That's what integration does. It adds up a bunch of continuously changing infinitesimal contributions. And we put in the expression for dA, and then we need the boundaries on the integral, and that's just from 0 to pi over 4. Now the integral of the tangent function is something that you may just have memorized. I wanted to cover this real quick as a side note. The way you get at the integral of the tangent is to write it as a sine over a cosine. And then I realize I have 1 over the cosine times the derivative of the cosine if I throw in a minus sign. And that comes from differentiating the natural log of the cosine function. It gives you 1 over the cosine, and then the chain rule tacks on the derivative of the cosine. So I end up with negative natural log, and this works for a plus or minus cosine in the argument of log, so I end up with these absolute value bars. And this can also be written by moving the minus sign into the exponent and writing it as the natural log of the absolute value of the secant of x. So using that formula for the integral of the tangent, I guess my antiderivatives over here, and I end up with a natural log secant x minus 1/2 x squared evaluated from 0 to pi over 4. And I don't have to worry about those absolute value bars because the values of the secant are all positive when x is between 0 and pi over 4. So when I plug in my lower limit, I get the natural log of the secant of 0. That's 1 over the cosine of 0. That's just 1. So the natural log of 1, and that vanishes. And when I plug in the 0 to the second term, it's 1/2 0 squared. All right, so both of those terms vanish when I plug in the lower limit, and all I have to worry about is my upper limit. And I get natural log secant pi over 4 minus 1/2 times pi over 4 squared. Then I just have to evaluate the secant of pi over 4. And the cosine of pi over 4 is 1 over root 2. So 1 over that is just root 2. And I have natural log root 2 minus 1/2 of pi squared over 16. So that's pi squared over 32. And the answer is really complete at this point. But I could write root 2 as 2 to the 1/2 and bring the 1/2 out in front. Write it as 1/2 natural log 2 minus pi squared over 32. Now, just out of curiosity, I'm going to get a decimal approximation on this, and I get approximately 0.04. If you find the math content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce dozens of new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.